This video will demonstrate the performance of a correlation coefficient, more specifically performing a Pearson product moment correlation coefficient for two related variables. We'll also look at creating a scatter plot to examine the data along with producing the R score or the R value associated with the Pearson correlation coefficient. So we have a couple of assumptions that we make when we do correlations, and again, typically we're doing a simple correlation. We're just trying to correlate two variables at a time, a bivariate correlation. And the assumption is that the measures are quantitative when using the Pearson correlation coefficient. Also that they're naturally occurring. In other words, we're not manipulating the situation at all. We're measuring variables that are naturally occurring. We're also assuming the variables have been measured without error and without bias. So in this case, what we have here are two variables. What we want to try and do is determine if there's a relationship between the average fluid consumption for a group of athletes and then the air temperature on that day of activity. So as you can see here, each pair of data points represents an average fluid consumption per person in ounces. So the average consumption was 50 ounces per person, and the temperature in Fahrenheit, degrees Fahrenheit, 90 degrees. The next time point represents the fluid consumption, again on average, 25 ounces per person on average on a 70-degree Fahrenheit day. So what we're going to try and do is determine if these two variables are related to one another. In other words, is the temperature of the air, or the temperature on that particular day of activity, does it explain or is it related to fluid consumption? Okay, so the first step in doing this analysis is to do a scatter plot. So we can try and examine whether or not we have a linear relationship, what type of relationship it is, whether it's positive or negative. Does it have a given form or shape to the relationship? Are there any outliers? And also to make sure it truly is a linear relationship versus a curvilinear relationship. So in order to produce a scatter plot, we go to the Graphs menu and choose Chart Builder. Okay, and then we're going to choose the chart that we want to create, and scatter or dot plot is our option here. And so we're going to choose just a simple scatter plot. So we choose that, and then we have to click and drag that option into the upper display box. Okay, and now you'll see it'll give us the option of indicating which variable goes on the x-axis and which variable goes on the y-axis. So we're assuming that there is kind of a time-dependent factor here. In other words, one variable has to come first before the other variable comes. In other words, we're assuming that one variable explains the variance in another. And in this case, temperature, we're assuming that temperature will explain fluid consumption. So we're going to click and drag temperature onto the x-axis so that we're using that as our explanatory variable. And then fluid consumption is our outcome, and we're going to drag that to the y-axis. Okay, now don't fear, this isn't actually what the scatter plot's going to look like. This is just a representation here. So once we've moved our variables over into their respective spots, we can click OK. And now in our output, we'll actually see the true scatter plot for those two variables. And so as we look at this scatter plot here, there's a few things we can look at. Again, each of these dots represents the convergence of the two data points. So here is temperature converging with the average fluid consumption. Now the first thing we can look at is form. Does it look like the dots are creating or taking the shape or creating a certain form? And as we look at this, we can see the dots do form somewhat of a straight line or a linear relationship from the bottom left to the upper right. Okay, that is one type of form they could take. They could be more like an egg shape or more an oval shape, but this is kind of the classic linear relationship or linear form that we very often look for. Now we also look at the direction of the form. Do the data plots or data points trend from lower left to upper right, or do they trend from upper left to lower right? In this case, they trend from lower left to upper right, so we would consider that to be a positive trend. If they trended from upper left to lower right, then that would be considered a negative trend. The next thing we can look at is how closely together the data points are to one another, or to kind of an imaginary line that we could draw from lower left to upper right. Okay, and as you can see, the data points are pretty clustered close together. If we were to draw kind of a balloon around these data points, it would be a very narrow balloon. Okay, if the balloon was much larger and much more oval shaped, then that would indicate kind of a weaker association. So far we can say that yes, there is a linear form to this relationship. It is a positive relationship, and it also seems to have a fairly strong strength of association. In other words, the data points are pretty close together. So it looks like we've got a relationship here that the Pearson correlation coefficient will be able to identify for us accurately and very specifically. And we also don't appear to have any outliers. We don't appear to have any dots that are separated a great distance from the other dots. So our next step then is to actually go ahead and calculate that R value, that correlation coefficient. So now we're going to go to the Analyze menu, and we're going to choose Correlate. And go to the bivariate option, because again we're correlating two variables, so bi meaning two. So we're going to choose that option, bivariate. And then what we need to do then is just make sure the variables that we want to correlate are in the variables box. Okay, so fluid consumption and temperature. We can go to the options box and make sure that we're going to get the means and standard deviations for each of these variables so we can report those descriptively. And then we also need to make sure that Pearson is checked, because that's the correlation we're attempting to do, and we've examined this data for the assumptions for a Pearson, mainly being that's quantitative and linear in its relationship. And we don't know what direction the relationship is going to go beforehand typically, so we're going to choose two-tailed testing, and that's going to be part of the hypothesis decision we're going to make. So at this point we also want to set a null hypothesis, and the null hypothesis would typically be that the correlation coefficient for these two variables would be equal to 0. In other words, there would be no correlation between them, so the R value would be close to 0. Now if we produce an R value that is equivalent to a p-value that is less than 0.05, then we'd be able to reject that null hypothesis. If the R value we calculate is equivalent to a p-value greater than 0.05, then we would accept the null hypothesis and say there really is no consistent relationship among these two variables. So when we're rejecting the null hypothesis, we're basically saying these two variables are related to one another. In other words, temperature seems to explain a significant amount of variance in fluid consumption. If we were going to accept the null hypothesis, we're basically saying that there's no relationship or an unclear relationship between these two variables. Okay, so once we've made those decisions, we can go ahead and click OK. And then we'll see the means for our two variables. So the mean fluid consumption over all of the particular data points was 29.2, and the mean temperature was 67. So first thing we want to look at is the actual Pearson correlation number, which is right here between fluid consumption and temperature, and that value is 0.978. And as we know, the closer the R value gets to 1, either positive or negative, then that indicates a very strong relationship. And as you can see, this is a very strong relationship, very close to the value of 1.0. We can also look at the p-value. That is quite a bit less than 0.05. And so we'd be able to reject the null hypothesis and say that there is a consistent relationship between these two variables, and that temperature seems to explain a significant amount of variance in fluid consumption. Now we can also look at the magnitude of this effect, or the magnitude of this relationship. In other words, what's the practical significance of this relationship? And how we do that is we do an R-squared value, where we take our R value, in this case 0.978, and we square it. So if we take 9.78 and we square it, we end up with a value of 0.956. So what that's telling us then is about 95% or 96% of the variance in fluid consumption is explained by temperature. So that's a very strong relationship then to say that there are some other things that explain the variance in fluid consumption, but there aren't, the influence of those other things is not very strong. So temperature seems to be a very strong explanatory variable for fluid consumption. So to summarize, we did the Pearson correlation coefficient for two quantitative variables. We wanted to make sure that the data was accurate, the data was complete, the data was normally distributed and unbiased in its measurement, and then we've been able to then use that to establish a relationship between these two variables. We looked at the statistical significance of this relationship using a p-value and also using the idea that the closer the r-value was to 1, the stronger the relationship. And then we also looked at the practical significance of this relationship by looking at the r-squared value, or what's known as the coefficient of determination.